This video is going to cover Chapter 8, but focusing on the weak acids and bases, mostly on quantitatively figuring out their pH or concentration. So what was mentioned in the last video with strong acids and strong bases are that strong acids and strong bases dissociate completely. So we're going to go with they break apart 100% into their cation and anion. So for acids, H plus, and then their negative charge, and then for bases, the positive charge, and then OH minus. But weak acids and bases dissociate, but just not 100% of the time. So usually it's something like less than 10% of a weak acid, of the weak acid molecules will actually dissociate into their H plus and negative charge. So we consider that as something that goes to equilibrium. So it dissociates to a certain extent, and then stays at those concentrations, although we know equilibrium, really the reaction isn't stopping, it's just continuing in the forward and reverse directions at the same rate. So from the textbook, this shows the weak acid dissociation equilibrium equation with the weak acid dissociation constant, the Ka value. And then for our weak base, this shows the equation from the textbook of the base accepting a proton from water, and we have the Kb, which is the base hydrolysis constant. I just usually call it the weak base dissociation constant. I like to look at weak acids where I include water into the equilibrium constant expression. So Ha is just representing all weak acids, well, all monoprotic weak acids, so have one hydrogen. So in this case, Ha is acting as the acid and water is acting as the base, because water is going to accept a proton while Ha is donating it. Okay, so then our Ka expression has hydronium, H3O plus, instead of H plus in it, what was on the last slide. And just a reminder that with equilibrium constants, the units we're using are molarity. The only other option is a pressure unit, which we're not dealing with pressures because all of our instances of weak acids and weak bases that we will be calculating are going to be aqueous. So they're solutions. So molarity is what those brackets are telling us. And then for Kb, the capital letter B represents the weak bases. In this case, well, the capital letter B is the base, and then water is the acid as it's donating the proton. So the base has gained a proton, so now it's Hb plus, it's gained an H plus, and then water, what is left is the hydroxide ion. So the equilibrium constant for the weak base looks the same as it was from the textbook. So I just have, I added water to the Ka expression. That's the difference between the textbook and what I have. So in terms of definitions, any weak acid has a conjugate base. Its conjugate base is just its version after it donated the proton. And a weak base, when it accepts the proton, has now become a weak acid. So like if we look at the last slide, where we have like the Ha, there we go, Ha, so that's a weak acid. Well, when it donates its proton, we have A minus. Well, that's its conjugate base because A minus can now accept a proton to turn back into Ha. So we have a weak acid. What is left is a weak base, but they are called conjugates. So for the weak base down here, it's a base because it can accept a proton. It's a weak base. After it accepts the proton, now it has a proton that it could donate, so now it's considered an acid. And these are conjugates of each other. The only difference between a conjugate acid and a conjugate base will be the absence or presence of an H plus. Okay. So for any acid, its conjugate base, we consider it a base. And any base, its conjugate acid, we consider an acid. So pretty much what that's saying is any positive charge, so cation, is going to be considered an acid, and then a negative charge, which are called anions, are going to be considered a base. Well, anions, negative charges, they could always accept a proton. They've got a negative charge. They've got a spot for an H plus to show up. The cation, any positive charge, could either, following the Bronsted-Lowry definition, if it contains a hydrogen, it could donate it, or if it doesn't, the Bronsted-Lowry definition of an acid is something that can accept electrons. Well, if it's got a positive charge, it could always accept at least one electron to make it neutral. The only exceptions to this are the conjugates of the strong things. So I have them listed up here. So these are the positive, the cations. The only cations that we do not consider weak acids are sodium ion, lithium ion, potassium ion, rubidium ion, and cesium ion, because sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide are the 5 strong bases. So they are so strong that their conjugate acids don't act like acids. So in terms of our anions, negative charges are considered weak bases. The exceptions to this, well, the bases of the strong acids. So we had the 5 strong acids, HCl, HBr, HI, HNO3, HClO4, so perchloric. We also had as a strong acid sulfuric, H2SO4, but sulfuric had that interesting situation where the first proton that dissociates is strong, but the second one is weak. So hydrogen sulfide, HSO4 negative, which is what is left when sulfuric acid donates its conjugate base. Well, that can still act as a base. It could accept that back, or it could act as an acid because it could donate the proton. Either way, it's not considered strong, so that would be considered a weak thing. So these, the 5 listed here are only anions, negative charges, that we are not going to consider weak bases. Okay. So for those of you that are taking or have taken organic, I know you've heard of carboxylic acids. So carboxylic acids are all weak acids. So their carboxylate, their conjugate base are all weak bases, because the carboxylic acid, that proton, the H there that's blue in the carboxylic acid, can be donated, so that makes it a base, it makes it an acid, but it's not considered a strong acid. It goes to equilibrium, it dissociates less than 100% of the time, so weak acid. So then its conjugate base is the carboxylate, so also a weak base. In terms of amines, again, those of you in organic, I know you've heard of an amine. They are weak bases, and ammoniums, when the amines gain a proton and become positively charged, those are their conjugate acids. So this is the weak base. That's not where I want it to be. Weak base. And so then their conjugates are weak acids. They have extra H pluses that they could then donate. Okay. So this is just reminding us of the Lewis definition. So when I mentioned that positive charges are considered acids, even though they have no protons to donate, they still can follow the Lewis definition of an acid, which is something that can accept electrons. It shows here that M just stands for any metal, any ion that has a positive charge, but it does specify that the charge has to be at least +2 or greater, so like +2, +3. That was really already taken care of when I listed the exceptions. Remember how sodium ion, lithium ion, potassium ion, rubidium ion, and cesium ion are exceptions to that? Well, they are the metals with a +1 charge. So that's why they're exempt from this. If we have a metal ion and one of them has a +2 charge and one of them has a +3 charge, the +3 charge, the more positive the charge, will be a stronger acid. It will more readily accept electrons because it's more positive. So this is how that Lewis definition, how that acid-base relationship happens. In this case, water has some electrons that it's willing to donate. That metal has space for electrons where no electrons are there. So when they bond, those 2 electrons are shared. These 2 electrons right here are coming from that oxygen, which is now sharing them with the metal, so it's donating them. The metal is accepting them as part of the 2-electron bond. Okay. So I showed you the definitions of Ka and Kb earlier. This is just giving us an example where ammonium, NH4+, is our weak acid, so they're being shown dissociated. And ammonia, NH3, is the weak base, and it's it's accepting a proton. So we've got the expression for the Ka and the Kb in those two cases. If we add these two equations together, what we're left with is this: water at equilibrium with H plus and OH minus. So there's a video that's entirely dedicated to discussing water and how it acts in terms of dissociating and how it affects the pH scale. So the equilibrium constant for that is defined as Kw, the equilibrium constant for water. And we actually gave that value a constant value, 1.0 times 10 to the negative 14th. That's actually only true at 25 degrees Celsius, but we're going to live with that. But just implying that, so when I added the equations together, we would have multiplied their equilibrium constants together. So this equation that I'm trying to box in right now allows us, if we know the equilibrium constant of a weak acid, we can solve for the equilibrium constant of its conjugate base. So this lets us convert a weak acid's dissociation constant to its conjugate base, or a weak base's to its conjugate acid. So that's a very useful equation, because sometimes we're given not exactly the information that we want, so we need to use this to convert it in the form we need. So what I have left in this video is just a few examples of us doing the math to solve for the pH for a weak acid or weak base. So I just have a couple examples here. So niacin, this chemical, we have a 0.02 molarity solution of it. And I'm telling you that the pH of this solution is 3.26. We're supposed to determine the equilibrium constant. So niacin is a weak acid. If nothing else, you can see it. If you look at the image that was provided, it's a carboxylic acid. So that proton, right there, that's the proton that will be donated when it acts as an acid. But any weak acid we can represent with HA. So I'm going to start this by writing out the equilibrium equation, just using HA to stand for niacin, because it's just the expression for a weak acid. So if I have HA plus water goes to equilibrium with H3O plus and A minus, that's our equilibrium constant expression. So we could write the equilibrium constant, or that was the equilibrium constant equation. We can write the equilibrium constant expression for Ka, products over reactants. So H3O plus times A minus all over HA. Remember, water is not part of this because pure liquids and pure solids are not part of the equilibrium constant. Water is a liquid. Okay. So hopefully we're all feeling okay on writing the equation at equilibrium and the equilibrium constant. In order to do the math here, we're going to have to do an ICE table, which is how we can be quantitative with equilibrium. So I in the ICE table stands for initial, C stands for change, and E stands for equilibrium. And we need to keep track of all the chemicals that are part of the equilibrium constant expression, which means I can ignore water, so I'm just going to draw a line. So we need to fill out all three rows for all of these chemicals, except for water, because we're trying to calculate the Ka value, and what we need are the equilibrium concentrations of these three chemicals. So we're looking for this equilibrium row. So I'm going to start out with the initial information. The only initial information I was given was that niacin starts out 0.020. We weren't told about hydronium or its conjugate base, so their initial concentrations must be 0. They were not mentioned. In terms of the change, well, what we know is going to happen is some of this HA is going to dissociate. So there's going to be, the change is going to be negative for the HA. We're going to lose some. Our equilibrium concentration should be less than 0.02 because the reaction has to go, to start out with anyway, left to right. That means that the hydronium concentration will have to increase, and then the conjugate base will also have to increase. I used x to represent that, and just remember that these x values, they're stoichiometric. So the coefficient tells you if it's 1x, like all of these, or 2x. If there was a coefficient of 2, this would be 2x. Okay. So in terms of equilibrium information, we weren't directly given equilibrium information, but we were given the pH. Okay, and the equation for pH that we've used is the negative log of the hydronium ion concentration. So isn't it possible for us to use this pH value to solve for H3O+? So that's what we can do here. To solve for H3O+, I can do 10 to the negative 3.26, and this is just me rearranging the pH equation. And what I get here, so it's got, the pH goes to two places past the decimal point. So my answer is going to have two significant figures. I don't want to round yet though, so I'm going to write 5.4. So there's my two sig figs. 9, 9, 5, 4. So those are not significant, but I just am keeping them. Times 10 to the negative 4th. And this is a molarity. So that is the molarity of hydronium ion once it's in solution and is allowed to reach equilibrium. So I'm going to write that in the equilibrium spot. 5.4, 954 times 10 to the negative 4th. So that means 0 plus x equals this number. So shouldn't this 0 plus x equal the same number? So I'm going to rewrite that. And then to figure out what goes here, I can do 0.020 minus 5.4954 times 10 to the negative 4th. And what I end up with is 0.01945. Okay, so I now have the equilibrium values of all three chemicals. So what I have left to do is take those values and plug them into the equilibrium constant expression so I can get a value. So it's going to be 5.4954 times 10 to the negative 4th for hydronium. Same number, 5.4954 times 10 to the negative 4th for the A minus, and then 0.01945 as my concentration of HA. So what I end up with, rounded to two significant figures, 1.6 times 10 to the negative 5. So there's our equilibrium constant. Okay, so another example of calculating with weak acids, in this case benzoic acid. This time though, instead of calculating the Ka value like the last example, we're going to determine the pH of the weak acid, which is actually the thing that we end up doing most often, especially when we get to chapter 9 and 10 when we're dealing with buffers and titrations. So in this example, benzoic acid is our weak acid. The hydrogen highlighted there, that's the hydrogen that will be donated. So it actually shows here an equilibrium constant expression showing benzoic acid, and it's like A minus, it's benzoate ion and it's hydrogen ion. But just to be consistent, I'm going to go ahead and rewrite the equilibrium constant expression only using HA to represent benzoic acid. Like I said, HA can represent any weak acid. Add water. Equilibrium with H3O plus and A minus. And then I'm going to go ahead and write the equilibrium constant expression. That's a K, in case you were wondering. H3O plus times A minus all over HA. And in the question it says we're supposed to calculate the pH. Well, like we used the equation in the last problem, the equation for pH equals the negative log of H3O plus. So in the last problem we were given the pH and we were able to use that to solve for the hydronium ion concentration. Well, in this case, since we're supposed to solve for pH, we need to know the hydronium ion concentration. Well, in the question, all we're given is what the molarity of the benzoic acid was initially, and then we have the equilibrium constant. So we need to solve for the equilibrium concentration of hydronium ion. So we're back to using an ice table again. And we once again get to ignore water. Any pure liquids or solids we get to ignore since they are not part of the equilibrium constant expression. And from the ice table, our end goal is to solve for the equilibrium concentration of the hydronium ion. So I'm just going to start at the beginning of the ice table. We were told that benzoic acid is 0.01000 molarity. We were not given any information about the other two. So we're assuming they start out with a 0 concentration. As with the last one, this weak acid has to dissociate, which means by equilibrium there will be less weak acid at equilibrium than there was initially. So it's going to do a minus X. It's a 1X because the stoichiometry is a 1 mole out front. So both of the products will be plus X. They started with 0, so there has to be more than 0 at the end. But what we don't have are any actual values to put in here as the equilibrium concentrations. We weren't told nothing. But we know that they will be, in this case, 0.01000 minus X. We just don't know what X is. We know that the hydronium ion will be whatever X is, 0 plus X, and the benzoate polyatomic ion will also be X. We just don't have numbers for X. So our goal right now is to solve for X. So what we can do is take the equilibrium constant value that we're given and plug it into our equilibrium constant expression, and then plug in these expressions for the equilibrium concentrations into the Ka expression, and use that equation to solve for X. So that's what I'm going to do. So for Ka, I'm going to put 6.28 times 10 to the negative fifth, substitute that in for Ka. So for the hydronium ion concentration, I'm going to say X. For A minus, I'm going to say X. And then 0.01000 minus X for the weak acid HA concentration. So now we need to take this equation, do some algebra to solve for X. So let's see, simplifying this a little bit, I'm going to move down here to the bottom. That X times X is an X squared. So I'm just going to write it that way. 6.28 times 10 to the negative fifth equals X squared over, oh that's beautiful, 0.01000 minus X. So we clearly see we have an X squared term. We're going to have a term with X to the first power, and then we have a value that has no X's at all. So we're going to end up with a quadratic equation. At some point in algebra, you have seen this format, and then you know the idea of using the quadratic equation to solve for X. So the quadratic equation, negative b plus or minus the square root b squared minus 4ac all over 2a. So what we need to do is get this expression into that format so we can follow the quadratic formula. So I'm going to, since I'm out of space, flip us over to the next slide and then just carry on from there. So I had 6.28 times 10 to the negative fifth equals x squared over 0.01000 minus x. So trying to get it in that 0 equals ax squared plus bx plus c form, I am going to pretty much cross multiply. I'm going to multiply 0.01000 minus x to both sides. So 6.28 times 10 to the negative fifth will be multiplied by 0.01000 minus x, and that is equal to x squared. So here I need to distribute. Multiply the Ka value times 0.01, multiply the Ka value times x. So that is going to give me distributing. So again, doing this times this, and then this times this. I'll have the x squared term, which is still alone, equals 6.28 times 10 to the negative 7th minus 6.28 times 10 to the negative 5th times x. Now I need to get it in the format the 0 equals ax squared plus bx plus c. So having this all equal to 0, 0 equals x squared plus 6.28 times 10 to the negative 5th x minus 6.28 times 10 to the negative 7th. So the a term, a term is equal to 1. The b term is equal to 6.28 times 10 to the negative 5th, and the c term is equal to negative 6.28 times 10 to the negative 7th. So now I need to do the quadratic formula. So negative b, so negative 6.28 times 10 to the negative 5th plus or minus the square root of b squared, 6.28 times 10 to the negative 5th squared, minus 4 times a, which is 1, times c, which is negative 6.28 times 10 to the negative 7th. So I'm going to expand all of that all over 2a, so 2 times 1. So now I've got some algebra to do. So I'm going to go from here. I'm going to have to go to the next slide because again I'm out of space. But I'm going to just do the math in here inside the square root and then take the square root of that value. And so what I ended up there, I had negative 6.28 times 10 to the negative 5th. That's my negative b, plus or minus, and then when I simplified everything inside the square root and then did the square root, what I got was 0.001586 all over 2. So I know with the quadratic formula you get two answers. This value plus this one, and then this value minus that one. Well, we're not in math class, we're in chemistry, so our results would not make sense for it to be a negative value. You can't have less than nothing in terms of molarity. So the minus, the answer I get by doing the subtraction, isn't going to be applicable here. So if I take negative 6.28 times 10 to the negative 5th plus that value and divide by 2, that'll give me an answer for x. And what I got was 7.61, and then I'm not going to round quite yet, so I'm going to keep a couple digits with me, 69, times 10 to the negative 4th. So that is the value of x. If I get all the way back to our ICE table, that's the x value that I can put in our ICE table. From our ICE table, the molarity of H3O plus at equilibrium, well, that was equal to x. X is equal to 7.6169 times 10 to the negative fourth. So I now have enough information to solve for the pH. I'm going to take the negative log of this x value. This had three significant figures, 7.61, which I guess would be rounding 7.62. So when I do the negative log of it, I should have three places to the right of the decimal point. So 3.118 is my pH value of a 0.01000 molarity solution of benzoic acid. Alright, I know this video is getting long. I have one more example. This one is a weak base. So in this case, we're calculating the pH of a 0.0351 molarity solution of the weak base cocaine. But you didn't know cocaine was a weak base. The Kb value is 2.6 times 10 to the negative sixth. So we're again solving for pH. Okay, so we know the equation for pH, but since this is a weak base, when I write the equilibrium constant expression, I'm going to use B to stand for cocaine or any other weak base, plus H2O, equilibrium arrows, and remember a weak base accepts a proton, so on the other side this is going to be Hb plus, the base with an extra proton, but that proton came from water, so what is left is OH minus. So I'm going to go ahead and write the Kb expression. It'll be Hb plus times OH minus all over the molarity of the weak base. So of these four chemicals in this equation, the one that is closest, that's the most useful in helping us find the pH, is actually going to be hydroxide ion. Remember there's a POH as well. So in order to get the pH, if I can figure out the OH, the hydroxide ion molarity, I am able to get to the pH from that point. So I'm going to need to set up an ice table where the number that I am most interested in to help me get the pH is going to be the equilibrium value of the hydroxide ion. So just setting up our ice table, I get to ignore water. I know the molarity of the weak base is given in the problem. The other two were not mentioned, so I'm going to start with zeros. Minus x plus x plus x, 0.0351 minus x, x, and x. So if I can calculate x, then I'll know the hydroxide ion molarity. So this one's very similar to the last problem that we just did. It's just working with a base. So what I'm going to do here is substitute the Kb value in, and then substitute in all of the equilibrium expressions into the Kb expression. So for Kb, I have 2.6 times 10 to the negative sixth. For Hb plus, I have x. For OH minus times x, so I'm going to go ahead and write x squared there, x times x. And in the denominator, 0.0351 minus x. So we once again have an x squared term, we're going to have an x term, and a term without any x's. So we're thinking quadratic formula. So I need to get this, do some algebra to rearrange this, so 0 equals all of my terms. So I'm going to have to cross multiply and do some distribution. I am not going to do every single step of that math for this problem. If you're having trouble with that, please come and see me. I'll happily go through all the steps for you. But what I'm going to go ahead and do is write the expression I got once I took this and used algebra to rearrange it. So I got x squared plus 2.6 times 10 to the negative sixth x minus 9.126 times 10 to the negative eighth. So A is 1, B is 2.6 times 10 to the negative sixth, and C is negative 9.126 times 10 to the negative eighth. So what I need to do is put this into the quadratic formula to solve. So flip into the next slide. What I'm going to do is I'm going to take those A, B, and C values and plug them into the quadratic formula. So negative 2.6 times 10 to the negative 6th plus or minus the square root. B squared, so 2.6 times 10 to the negative 6th squared. That's a negative 6. Minus 4ac, so a is 1, c is negative 9.126 times 10 to the negative 8th. And this is all inside of the square root. And then this whole thing over 2a, so 2 times 1. So we're going to be in the situation again where the subtraction term in this quadratic formula is not going to be relevant to us in this situation because you do not have a negative molarity. So when I did the algebra and I simplified this, the value that I got for x, which is just using the plus term, was 3.0. I'm just going to keep a couple extra digits for now. 0.795 times 10 to the negative 4th. Okay, so from the ICE table, the hydroxide ion molarity at equilibrium is equal to x. We know x is equal to 3.00795 times 10 to the negative 4th. So the point of this problem is to calculate the pH. Well, I have the hydroxide ion molarity, not the hydronium. So my approach is going to be to determine the pOH, which I get from taking the negative log of the hydroxide ion. So negative log of 3.00795 times 10 to the negative 4th. And what I got there was 3.52, 2 sig figs, so 2 decimal places to the right. 173 are little numbers. But I need to get this to pH, not pOH. Well, pH plus pOH equal 14.00. So to solve for pH, if I take 14.00 minus 3.52173, what I get is 10.4783, so 10.48 as my pH. So the difference between the second problem we did and the last problem was just a weak acid to a weak base. The math was very, very similar. Just be careful with the weak base that you remember that the ICE table itself does not contain hydronium. It doesn't have H3O+. So you've got to remember that it has hydroxide. But otherwise, very, very similar. All right. Yay for Chapter 8.